Hi, it's me again, back for the final video in this short 4 videos series about what actually is electricity, so that when you're learning about electricity at school you haven't got to hold some weird concept in your head about lorries dropping off parcels at shops and going back to get some more and all this other kind of stuff, because we actually understand what is going on with electricity, with the electrons that are moving around. So that was in the previous videos. This video we are going to look at something called the motor effect. Now last time we learnt that electricity and magnetism are very closely entwined, and that we thought of electrons in a wire like lots and lots and lots of mini magnets. So in this wire here we have got millions and millions of electrons that are all behaving like magnets, but they're all pointing in different directions, so their magnetism isn't sort of adding up and all pulling in the same direction. And that if we send an electric current through it, we make all the electrons sort of point in the same direction, so all their little magnetic fields all point in the same direction, and it starts to build up into something that we can use. So what I've got here, I've just got a loop, quite a long loop of wire, which is connected to a power supply here. And what this power supply will do, when I will turn it on, it will just send an electric current through this wire. And I send electric current through this wire, and this wire becomes a very weak magnet all over the place. And we said last time if we coiled it all together we could concentrate that magnetism to make it useful. Now this actually is a permanent magnet, so this has its own magnetic field going from the North Pole to the South Pole here. And what I'm going to do, I'm going to hold this piece of wire in this magnetic field so we can see what's happening, and then I'm going to turn the electric current on and see what happens. And you can see that piece of wire moved out of the field there. Let's turn that off and do that again, so now we know what we're looking at. So if I hold it like that, I turn it on and the wire moves out of the way of the field. If I was to turn the magnet the other way, so the magnetic field is going the opposite direction, what do you think will happen when I turn it on now? It moves inwards. So as I turn this on, it moves the wire. If I was to turn the magnet over, so the magnetic field is going the other way, the wire moves outwards. Let's do it so that we can see a little bit better. So the wire moves outwards. If I was to take my electric current and swap this over, so I sent the electricity the other way around the circuit, now all of a sudden that starts moving inwards there. So if I change the direction that the current goes around the circuit, this piece of wire moves in a different direction. And from this, from the fact that we have got electricity and we have got magnetism, we put the two together and we get movement. So things move with electricity and magnetism, and that's how we can get motors and all sorts of things. And once we can make things move with electricity, then we're literally on our way. So when you do your physics in class, you will learn about something called Fleming's left-hand rule, which is this thing here. And all this does is it tells you which way the thing is going to move. I've got my magnetic field, which is going from top to bottom here. So that's going in one direction. And when I put my electric current in here, that's going across the direction of the magnetic field. Magnetic field's going that way, current's going that way, and then the movement goes that way. So all these 3 things are all at right angles to each other. And this little thing here, it tells you which way it's going to move. They'll ask you this in the exam. So your first finger, that's a F for first, that is the direction of the magnetic field. So if the magnetic field is going that way, you point your finger that way. If the current is going downwards, that's your second finger, C for current, C for second, goes down that way, then the thumb, which has got an M in it for movement, means that the wire is going to move out that way. So they all move at right angles to each other. If you turn the current the other way, so it's going that way, you've still got your field that way, but now the current's going up, and this time the movement goes that way. So anyway, that's just a bit of physics that you will get to do in your lessons. Now back to this thing. So this is in a magnetic field. With a current in there, it moves. If I change the direction of the current, it moves the other way, because the sort of virtual magnet in here goes the other way. So what happens if I connect it to what I call an alternating current? Now the alternating current, the electrons don't go round in one direction around the circuit, they go backwards and forwards, so they're constantly changing direction all the time. So what will happen here if it's constantly changing direction? And here you can see that it vibrates, it moves first one way and then another way as it's shaking inside this field, because the current is changing direction all the time. Now, as before, if I was to coil this up, we could concentrate all of this and we get a little bit more movement, because it's an alternating current, electrons going backwards and forwards, constantly changing the direction of the magnetic field and the movement. So we got that. What if I didn't have that and I didn't have this, but instead I had a thing that I've made here. Now, what I've got here is a coil of wire. Now, we said before that when you coil wire around, you concentrate what's going on. So I've got a coil of wire, and if I send electricity around that in one direction, that becomes an electromagnet. We did that last lesson. If I change the direction of the current and it goes around the other way, the magnet turns around. So if this was a north pole at the top, when I send the current the other way, all of a sudden it becomes a south pole. And so if I'm sending an alternating current backwards and forwards through this thing, the magnet is going to be going virtually turning upside down. So north pole here one moment and then a south pole here the other moment. Now you've got that. Now if we have my little magnets, here we are, I keep losing stuff here. If I have a magnet here, and it's a tiny wee little magnet, if this is a north pole here, at some point it will attract the magnet. But if the electricity goes the other way and this becomes a south pole, that might repel the magnet. So this magnet here will be moving backwards and forwards towards this thing in time with the rate that the current is changing direction. So if the current changed direction in time to some sound, for example, so I've got here, I've got my phone, and if I was to play some music on here, then there's the sound that comes out of here is actually an alternating current going backwards and forwards in time with the music. So now I've got an alternating current here. I've got a little circuit board and an amplifier just to make it bigger because it wasn't working. It's not really powerful enough. So now I've got an alternating current going backwards and forwards around here in time with the music. Right, so where are we going with this? Now I've got a little plastic cup. I'll put a little magnet in the bottom of the cup there, and I've got another bigger magnet on there, and if I bring this towards this, I turn the power on, something should happen. So what we're doing is this magnet is being sucked towards my little electromagnet, my little coil, one moment, and then the next moment it's being pushed away. So it's like sucking and blowing towards it, and it's making the bottom of this cup vibrate backwards and forwards, and so that is making the air that's inside there vibrate backwards and forwards. And so, as you know, vibrating air is sound, and that's how loudspeakers work, and that's how the speakers in your headphones and everything like that work. So I had that there. I could have a bigger cup. Let's have this bucket here. I've still got my little magnet on the bottom, and it's held in place by a tiny magnet inside. And let's go back and start this thing here. Let's try that again. That's not bad, is it? We could learn some equations, couldn't we? Hey you, the FNCU crew, here's some learning for you to do. Get your equations, remember them good, then show off your marks to the boys in the hood. Electricity first, then some forces. You need to know them all for your physics courses. Volts is current times resistance. You must learn it well. It's my insistence. Energies, PD times charge. Coulombs and volts equals joules that are large. Charge, it's current times time. It's all the electrons that flow down the line. Write them down. nailed to the door. Now get ready to do some more. Kilowatts, megawatts, watts is power. Divide energy by time in seconds, not hours. Need more power? Light the lamps. Multiply the volts by the amps. For power equation number 3. We thank Bob Marley, as you will see, because I will see you through. If you multiply by resistance 2. We're done with sparks, now pushes and pulls. Here come the forces. Learn the rules. Velocity is first to check. Distance over time in meters per sec. Each generation must know acceleration. Spread the word across the nation. Remember this, and you'll be fine. It's change in velocity divided by time. But with the units, you must take care. Acceleration is meters per second squared. Heavy things are hard to stop and move away. Remember, Isaac said F equals ma. Density is heaviness in a certain space. It's mass over volume to make the scientific case. One new thing I have to mention. It's equation about a spring's extension. Times by k to get the force. Springs aren't all the same, of course. Mass times gravity makes your weight in newtons. Get your units straight. Gravity, energy can be found. Just multiply the weight by the height above ground. Kinetic energy will move me with a half an m and a v times v. If you do some work, you're using joules. That's force times distance, you crazy fools. If it's moving, it's got momentum, it's always conserved. You never spend them, it's mass times velocity in kgm stroke suc. We're not done yet, a few more fish in the sea. Let me tell you about efficiency. It's good stuff out over total put in. Energy or power, it's all the same thing. A moving wave has a certain speed. Frequency times wavelength is the answer you need. Learn all this and your physics will be hot, as the Onions say. That's it, that's your lot. That was a FNCU rap. When you do your GCSE physics exam, you need to know about 20 equations, and they're all in there, and that will be on another video, so watch out for that one. Okay, I'll catch you next time. Bye now.